Hi, everyone. Thank you for coming. My name is Noah Saylor. I am a second-year grad student at UC Berkeley, in the physics department. But I work in a cosmology group, and I wanted to share a talk today about the prospect of measuring neutrino masses with cosmological data kind of in the next 10 years or so. So yeah, let's jump right into it. So I'm assuming that there are plenty of people in the audience who have no idea what a neutrino is. So I wanted to start with the basics, with what they are. Neutrinos are fundamental particles, meaning that they're not made up of anything else. They're not composite. They comprise 3 of the 17 fundamental particles in our standard model over here on the right. We know that they aren't electrically charged, so they don't, repel electrons in the same way that an electron repels another electron. But they do interact with ordinary particles through something called the weak force, which is important for processes like nuclear decay. The reason why these guys are so interesting is because we know very little about them. For example, some of the interesting questions about them are, are they their own antiparticle? This is something that we haven't figured out yet. And if it's true that they are their own antiparticle, this could be a key in understanding why in the universe we see more matter than antimatter. But I might be getting a little bit ahead of myself, so I just wanted to talk a little bit about how we know these things exist and kind of the history behind how we predicted and then eventually found these guys. So the way the story went was that neutrinos were predicted before they were actually discovered. In the early 1930s, a physicist named Pauli was studying this process called beta decay, which is basically when a neutron in an atom decays into a proton and an electron. And at the time, that's all people thought the neutron decayed into, was those 2 things. Now, Pauli was looking at the momentum of these decay products, the momentum of the proton and the electron, and then he added them, and he found that the sum didn't equal the momentum of the neutron. So somehow momentum was being violated. And Pauli's clever trick for kind of rectifying this problem was to invent some other particle that was carrying away this missing momentum, which later became known as the neutrino. From these momentum calculations, he knew that the mass of the neutrino had to be really small, no bigger than 1% the mass of a proton. And he famously said that he's done a terrible thing. He's kind of postulated or invented a particle that cannot actually be detected because these things, to the experiments at the time, were completely invisible. But that didn't stop experimentalists. And 20 years later, these things were finally detected. The way that it wound up working is that you took a nuclear reactor and you stuck it next to a giant bucket filled with water or whatever. And as the uranium in that reactor decayed into smaller atoms, those atoms then underwent beta decay and produced a ton of neutrinos. And these neutrinos, very infrequently, would collide with one of the atoms in your detector and then go through this reverse beta decay process where you have a neutrino over here coming in and interacting with a proton and then producing a neutron along with an electron, for example, or an anti-electron. Okay, so that's great. We've discovered them. Now we know that there are actually 3 of these guys. They correspond to different flavors. So when a neutron decays, it can go to a proton and an electron. It could also go to a proton and a muon is just a heavier version of the electron. Or it could go to a tau, which is just a heavier version of the muon. And so that, in a similar way that there are 3 different flavors here for the lepton, you can have 3 different flavors for the neutrino. So it can either be electron flavor, muon flavor, or tau flavor. Even more recently, we discovered that these neutrinos have mass. And the way that we discovered this was kind of through a not totally obvious experiment, where we noticed that these neutrinos actually oscillate flavors. They change flavors as they move through spacetime. Okay, so how does this mean, or how do we draw from this that these things have mass? Well, in quantum mechanics, when you have a state of definite energy, meaning that if you measure the state of the system, you get the same energy every time, that state ends up not evolving over time. Okay, so that's kind of what we know from quantum mechanics. And since we've observed that these neutrinos oscillate, it means that they can't be states of definite energy. This means that they're in something called a superposition of energy eigenstates. are states of definite energy. Okay, and we know that these states have to have different energies. So that means that not all of the neutrinos can be massless. So there needs to be some mass there. The way that these oscillations were detected was by looking at these neutrinos in the atmosphere. So over here you have your little bucket, and you're looking at neutrinos coming from the atmosphere over here, and neutrinos coming from the atmosphere over here. And these neutrinos have to travel different distances to get to your bucket. And so because of that, they have different oscillation signatures. So if you started out with all electron neutrinos, the distribution of the neutrinos that you get from these two different parts of the sky will end up looking different. And so this is kind of how we discovered that they oscillate, which eventually led to us understanding that they had mass. All right. We know that from these oscillations, a lower bound on the mass of these neutrinos, which is 60 millielectron volts. And it's believed that the actual value for the sum of these three masses is somewhere around 100 millielectron volts, which, to put this in perspective, is 10 million times lighter than the mass of an electron. So they're super tiny. All right, so neutrinos have mass, but we don't know what the actual value is. It turns out that these oscillation experiments, they only measure the difference squared between different masses of neutrinos. And so from that, that's not enough in order to reconstruct what the individual masses M1, M2, and M3 are. And it would be really nice to know what these are, because then we would be able to better understand the oscillation properties and the mixing behavior between different neutrino flavors and different neutrino masses, and help to understand, this corner of the standard model a little bit better. So something that's almost as good as measuring these individual masses is measuring the sum of these masses. And this is something that cosmology ends up being sensitive to. And these next few slides are supposed to be an overview of kind of how that ends up working. Over here on the right, I have different kind of hierarchies. This is just to show that we don't even know the ordering of the neutrino masses. So we don't know if, the muon electrino, or muon neutrino is on average heavier than the electron neutrino. That's kind of how clueless we are at the moment. All right, so neutrinos and cosmology. I'm assuming that some people have no idea what cosmology is, and kind of the definition of it is relatively simple. It's just the study of the evolutionary history of the universe. So we have this idea of how the universe kind of evolved over time, is that it started with a bang, and that there was this continued expansion that was decelerating for a while, and then recently started to accelerate due to this dark energy. And all along, there have been this structure formation. So galaxies started forming, galaxy clusters and planets and humans and whatnot. All right, so how do these little tiny neutrinos that are almost massless end up having an effect on something as large as the observable universe and how it evolves over time? And the answer is that the Big Bang produced a ton of these guys. In the Big Bang, there was this thermal bath of particles that was produced, including neutrinos and other things like electrons and photons and whatnot. And from this bath, today, there are still 100 neutrinos per cubic centimeter anywhere in the universe. It doesn't matter where you are. And these neutrinos, these leftover neutrinos from the Big Bang, are called the cosmic neutrino background. And they're what's important in terms of, to a cosmologist, in terms of evolving or studying the universe's expansion history. So this is what neutrinos actually do in an observable way, is that they damp structure. So over on the right-hand side here, I have two different plots. The colors are supposed to be just the amount of mass that you have at a particular point in space. And on the left here, we have a universe where the neutrinos are massive. And on the right here, we have a plot where the neutrinos are massless. And you see that in the left, the matter is spread out more. You don't have quite sharp peaks as you do right here, where you might have a cluster of galaxies or a galaxy or something. And so intuitively, this is what's happening. Neutrinos are damping structure. They do this because in the early universe, when temperatures are super, super high, the energy density of neutrinos is dominated by their kinetic energy, and they basically behave like massless particles. These massless particles end up just going into gravitational potential wells and shooting right back out of them they don't cluster in the same way, you know, a galaxy will want to cluster with another galaxy under gravitational attraction. As a result, you end up having just this kind of scale dependent, independent, or constant energy density due to this blanket of neutrinos that's not clustering. And this blanket of neutrinos acts as kind of like a friction force, and it slows down the clustering of ordinary matter, ordinary galaxies and stuff that we're used to. And the strength of this effect, the strength of this dampening, is proportional to the energy density of the neutrinos, which at late times, once neutrinos have lost all of their kinetic energy, is entirely due to their rest mass. This isn't the idea of like E equals mc squared. And so the mass of these neutrinos is ultimately what's controlling kind of the damping of this structure growth. This, you know, yeah, this process where you don't get quite as sharp peaks in structure formation. So that's great. I told you what neutrinos actually do, but how do we actually measure this with real data? This is just simulated data, by the way. This is real. And so the idea is to find observables that happened at two different points in time, and then compare the fluctuations of kind of the matter or energy distribution in the universe at those times, and connect them with a theory, which we have, called the Einstein-Boltzmann equations, and then ask, what value of the neutrino mass do I need in order to fit the data? And so this is ultimately what we end up doing. And what we use for these two different timestamps are the cosmic microwave background, which is produced around 380,000 years after the Big Bang. And then for local measurements, measurements of events that are happening kind of in the near past, we use galaxy clustering of galaxies that aren't too far away. And by comparing kind of the size of the fluctuations here to the size of the fluctuations here, you can begin to tease out what the neutrino mass ought to be. So I'm assuming that the people are kind of familiar with galaxies and could, you know, relatively have a good intuition on like maybe there's more galaxies here and fewer galaxies in this void and that kind of idea. But I'm also assuming that not many people know about the cosmic microwave background, so I wanted to have a quick slide to explain what that is. So remember, I told you that the Big Bang produces this bath of particles, and including neutrinos, but also photons, which are just the kind of quantum version of light, little discrete packets of energy. And in the early universe, remember, temperatures were high, and they were so high that you couldn't have atoms. An electron would have so much kinetic energy that it would just scatter off of a proton whenever it interacted with one. Because of that, you had just all of these free electrons everywhere in your universe. And so a photon traveling along would just scatter off of a free electron. And so the universe was more or less opaque. But around 380,000 years after the Big Bang, the universe cooled enough so that neutral hydrogen, which is just a proton and an electron, the electron had slowed down enough that it was able to be captured by the proton. And so you actually had these atoms, you had fewer free electrons, so the photon stopped scattering. And so now you have all of this light left over from the Big Bang that's now just free streaming. And this is light that we can still observe today. It was discovered in the late 60s. And we're building bigger and better experiments to make cleaner and cleaner maps of this process. And kind of the temperature of these photons, the temperature or the intensity of this light, it traces the matter distribution. So in regions that are red or regions that are blue, you have more or less matter. And so from here, you're able to estimate kind of the fluctuations of, you know, having matter at different length scales. All right, so now we're experts on the CMB. So now we can start to ask questions like, how big is this effect of going from the CMB fluctuations to the fluctuations we see today in galaxies? How big of an effect do neutrinos have on damping this? And it turns out that this effect is super tiny. So in this plot here on the y-axis, I have kind of the amplitude of fluctuations as a function of the length scale that I'm looking at. So over on the left here, I have huge length scales. So maybe those length scales span like the entirety of this box. And then on the right here, I have small length scales, which might be just like the length scale of one of these filaments here. And you can see that, in this plot, what neutrinos end up doing is they end up damping the amount of fluctuations that you have at these smaller length scales. And this effect for realistic values of neutrino masses is only like a % level effect, which means that you have to be able to measure these fluctuations to better than a % in order to actually detect the effect of neutrinos. Now with current data, with current CMB data and current galaxy clustering data, we can only put upper bounds on the neutrino mass. Our error bars are too large, and so we're not actually able to get a measurement. And so we know that neutrino mass has to be less than 120 MeV or so. Combined with the oscillation experiments, this means that the sum of the neutrino mass has to be between 60 and 120 MeV. But we want to do better. We want to turn this inequality into something that's actually a measurement. And in order to do this, we need better data. Unfortunately, there's lots of good data coming within the next decade. So my first experiment that I wanted to talk about is just something called Simon's Observatory. This is a next generation CMB survey that's comprised of 4 telescopes, this big one over here. So for scale reference, this thing here is about the size of a human. So this entire telescope is massive. That's a 6-meter diameter aperture. And then there are 3 of these smaller aperture telescopes. Here's a human and also a penguin for scale reference. Together, these things have over 60,000 superconducting pixels, which are designed to be incredibly sensitive to microwave light. And they're enclosed in these cryostats so that everything surrounding them is super cool, so that the kind of black body radiation that's given off by the surroundings don't end up interfering with your signal, which is the cosmic microwave background. This is a huge collaboration that covers, multiple continents with dozens of universities. The actual experiment is located in the Atacama Desert in Chile, and it's at an elevation of 17,000 feet. So you're huffing and puffing when you're bolting screws and stuff together in order to build these things. The reason why it's up so high is that it's high and dry. So you have less atmosphere to look through, and you don't have to worry about clouds messing up your map. And this thing is currently being built, and it's set to do its first observations kind of in the next 2 years. So on the other side of the coin, for measurements of these matter fluctuations that are kind of more near past or nearer to the present, there's this experiment called the Dark Energy Spectroscopic Instrument, which is kind of just started observing. It's in Arizona, again, at a high altitude, not quite as high, but still pretty high up there. And this thing is going to image tens of millions of galaxies in the next 5 years. And as you image more and more galaxies, kind of the error bars on this plot here of the amplitude of fluctuations as a function of scale goes down. So they get smaller and smaller, and you become more and more sensitive to this effect of neutrino masses. So within this decade, we're going to have both Simon's Observatory and DESI data, which is really exciting and something that I'm looking forward to working on. I'm both a member of ESO and DESI. Current forecasts suggest that with this data, we'll be able to achieve error bars of something like 20 MeV. Now remember, from oscillation experiments, we know that the mass of neutrinos has to be larger than 60 MeV. So this means that if you plotted your point, it's 60 MeV, and then you had 20 MeV error bars, 0 is no longer within your error bars. So we go from just having this lower bound or upper bound from cosmology to now actually having a measurement, which will be super exciting. Some of the kind of immediate consequences of this is that we're finally going to be able to answer the question of their ordering. So if you measure a neutrino mass that's less than 100 MeV, it turns out that this inverted hierarchy is more or less ruled out. And so then the ordering, that's really nice. That helps you kind of determine some of the properties of the neutrinos. And then also just knowing some of the masses helps you constrain some of the other mixing properties between different flavors and masses of neutrinos. That being said, there is a lot of work that's left to do in order to make this happen. Obviously, you have to finish building the experiments, and once they're built and start taking data, you have to do a lot of processing in order to actually get decent maps. There are lots of systematics that are involved with making this measurement. There are other physical effects that damp the amplitude of these fluctuations. And so you have to understand those different effects, and you have to, filter them and make sure that you're making a clean measurement. And then along with that, there is definitely improvement that can be made in the theory modeling to better understand these effects of neutrinos, especially at really, really small scales, which ends up being much harder to predict. So that's kind of where I wanted to end it. The moral of the story being, this is an exciting science goal that people have talked about for a while, and kind of within the next 10 years, we're actually going to be able to start answering questions about what the sum of these neutrinos actually are. So with that, I am happy to answer any, oh, great, I already see questions. All right, so first question, is the anti-neutrino the antimatter version of the neutrino, like a positron? That's exactly right. Ooh, how many Planck lengths long is a neutrino? I don't really know. I'm not sure how exactly to answer this question. When you have something, so in quantum mechanics, when you have a state of definite momentum, so you know the object's momentum, the way that you describe it is with a wave-like feature, and at that point, it's a little hard to talk about something like a neutrino as if it's localized to one point in space. And so you mostly describe it by its wavelength. If you really want to kind of calculate what that wavelength is, it's something like Planck's constant over the momentum. So I'll let you plug those numbers in and see what you find. How far away is the closest neutrino to us? There are neutrinos inside of you right now, for sure. There are millions of neutrinos that are passing through your body every second. Unfortunately, they don't, or fortunately, they aren't scattering too much. That could be a big problem if you end up having a bunch of neutrinos colliding with the atoms in your body and then them scattering. Definitely not healthy. Enraged Alex, I like the name. When was the neutrino made during the formation of the universe? So far as we know, neutrinos were made at kind of the beginning, after this period of rapid expansion that we call inflation, that as kind of the energy from that rapid expansion decayed, it decayed into all sorts of particles, whether they be electrons, photons, and neutrinos, and kind of, so they were formed basically at the beginning at the same time as electrons, or at the same time as photons. Does neutrino mass affect dark matter theories? Not that so neutrinos having a mass do affect the way that dark matter clusters, but I don't think it has to. I don't think it has to fundamentally change the way that dark matter works. So neutrinos interact indirectly with dark matter because of gravity, but neutrinos having a mass doesn't mean that dark matter has to be fundamentally different. So do neutrinos interact with each other? Yeah, they can interact indirectly. They definitely can. Why can't we measure neutrinos that are around us? So the short answer is that you can. The long answer is that it's just really unlikely. So these things do interact. It's just very infrequently. And the way that you detect them is you just build a giant bucket. It's kind of a philosophy of you can't change the probability that they're going to interact. So you're just going to build more stuff so that the probability of them interacting with something goes up. So it does happen, it's just extremely infrequently. I understand the new instruments will allow us to measure the sum of neutrino masses more precisely. How does this help us determine the individual neutrino masses? It doesn't. This is something that, oops, I've lost my questions. Oh boy. Yeah, so the individual neutrino masses is still a mystery. It's just, with cosmology, you get a complementary measurement. Instead of measuring differences squared, you're measuring the sum. And ideally, you would just want to have all three individual masses. But with differences squared in the sum, you can kind of start to get a better idea for what those masses should be, just kind of using algebra. Let's see, maybe I can share my screen again and point here. So for example, like with oscillations, you just measure the difference between, neutrino 3 and neutrino 2. But you don't know where on this y-axis you should even start, because you don't know the overall mass of these things. But if you know the sum of these neutrinos and you know the differences squared, then you can figure out where on this y-axis neutrino 3 should be, and then kind of go down the line and you figure out what the mass of neutrino 2 and neutrino 1 are. So, but yeah, at that point, it's just a little bit of algebra. Has neutrino-based communication been successful? So far as I know, nobody has done that. So no, I don't think it's been successful yet. Can neutrinos travel at the speed of light? No, they don't. They travel, super high fraction, almost 100% of the speed of light, but not quite there. Why are we interested in neutrinos? Yeah, that's a great question. For practical purposes, I don't think that there's going to be huge practical implications of figuring out what the neutrino masses are. I think it's more just an inherent curiosity question of realizing that these are objects that are completely fundamental. They're not made of anything else. They exist and they're out there, and they have these properties that we don't quite understand, and we just want to understand what they are. In terms of other interesting kind of consequences of neutrino masses, one of them is that if neutrinos end up being their own antiparticle, that could be a possible source for explaining why in the universe there's more matter than antimatter. And understanding the neutrino masses helps us better answer this question by constraining the relationship between kind of states of neutrinos that have definite mass and states of neutrinos that have definite flavor. So it's kind of one piece of that much larger puzzle. Do you think that neutrinos could be made of smaller particles, or is it proven that they're fundamental? It's definitely not proven that they're fundamental. It's not proven that any of the particles in the standard model are fundamental. So they could very well be made of anything else, of something else. If I don't think that there is necessarily a great fundamental reason for why neutrinos should be made of something more simple. I think at this point we just don't know. Some people think that they're made out of strings. Other people don't. Let's see. Are there any experiments planned to compute individual neutrino masses? Let's see. It's at 3:30 p.m. Okay. So far as I know, there aren't any straightforward ways of doing that. Kind of the two major things are these oscillation experiments, and then these experiments where you measure the sum of the neutrino masses through cosmology, and then you kind of reverse engineer what the individual masses are. Is there any way to trap neutrinos? I don't think anyone has been able to do that. I think that would be extremely hard. Usually when you're trapping something, like a molecule in a usual, like, using like optical tweezers, you're trapping it because you're sticking it in some potential well. And the reason why it stays in that potential well is because it interacts strongly with the thing that's causing that potential well. And because neutrinos very infrequently interact with anything, the size of that potential well would need to be massive. So no way of trapping neutrinos that I know of that would be practical at all. It would be very cool if you could do it. Let's see, are there any more last second questions? Or if not, I think we've run over just a little bit.
Thanks so much, Noah. That was super awesome and really interesting. I think with that, we can wrap up the session. Thank you all for attending.